lot of people imagine vulnerability management as a purely technical chore, like a never-ending list of flaws that security teams chase until they get tired. In this episode, we're going to make vulnerability management for AI systems feel clearer and more purposeful by treating it as a disciplined habit that protects trust over time. AI systems have vulnerabilities that look like classic software problems, but they also have vulnerabilities that come from data flow, model behavior, and integrations that turn outputs into actions. When you are new, it can be confusing to separate a bug from a risk from a weakness, so we will keep returning to a simple idea. A vulnerability is a weakness that can realistically be exploited or can realistically cause harm in your environment. The goal is to build a complete vulnerability management cycle that starts with discovery, continues through validation and prioritization, and ends with remediation that is verified and documented. When you can run this cycle calmly, you stop being surprised by weaknesses and you start improving the system's safety as a routine part of operating it. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Vulnerability management is the ongoing process of finding weaknesses, understanding them, deciding which ones matter most, fixing them, and making sure the fixes stick. The reason it matters is not because you can eliminate all vulnerabilities, but because untracked vulnerabilities quietly accumulate until one becomes an incident. For AI systems, the weaknesses can sit in many places at once, including the application layer, the model interface, the retrieval pipeline, the data sources, the output channels, and the vendor services that supply key capabilities. A beginner should notice that vulnerability management is not the same as incident response, because vulnerability management happens before harm is confirmed, while incident response happens after you have signs of harm. Vulnerability management also differs from general risk management because it focuses on specific weaknesses and the concrete steps to reduce them. When done well, vulnerability management becomes a predictable conveyor belt that turns unknown risk into known work and known work into safer operation. That conveyor belt is what keeps AI systems from becoming fragile as they evolve. AI vulnerability management begins with discovery, and discovery means building reliable ways to notice weaknesses rather than hoping someone stumbles upon them. Discovery can come from security testing, from monitoring signals, from user reports, from audits, and from change reviews that reveal new exposure. It can also come from noticing patterns like repeated policy boundary probing, surprising outputs that suggest retrieval is too broad, or error patterns that suggest an integration is failing open instead of failing closed. Beginners sometimes assume discovery requires rare expert creativity, but much of discovery is routine observation paired with curiosity about what should not be happening. A practical mindset is to treat every anomaly as a question, then decide whether it is a quality problem, a safety problem, or a vulnerability that could be exploited. For AI systems, anomalies can include the model revealing internal instruction fragments, retrieving documents outside intended scope, or responding differently for different users in a way that suggests role boundaries are weak. Discovery is successful when it is continuous and repeatable, not when it is dramatic. Once a potential vulnerability is discovered, the next step is triage and validation, because not every reported issue is real and not every real issue is exploitable. Validation means confirming what happened, under what conditions it happened, and whether it can be reproduced. With AI, reproducibility can be tricky because outputs can vary, so validation often focuses on whether the weakness is systematic, like a retrieval boundary that is consistently too broad, rather than whether the exact same wording appears every time. A beginner should also understand that validation includes checking scope, such as whether the weakness exists only in a test environment or also in production, and whether it affects one feature or many. Validation should also include evidence collection, like capturing the prompt pattern, the retrieved context indicators, the output, and the related logs that show who accessed what and when. The purpose is to move from a vague complaint to a precise description of the weakness that an engineering team can act on. When validation is done carefully, it prevents wasted effort on false alarms and prevents underreaction to real exposure. A distinctive part of AI vulnerability management is classifying vulnerabilities in a way that matches how AI systems create harm. Some vulnerabilities are classic application flaws, like insecure access control, weak authentication boundaries, or misconfigured logging that exposes sensitive records. Some vulnerabilities are data flow weaknesses, like retrieval systems that return documents beyond the user's authorization or pipelines that attach sensitive fields to prompts unnecessarily. Some vulnerabilities are policy enforcement weaknesses, like filters that can be bypassed with trivial prompt changes or refusal behavior that is inconsistent enough to be exploited. Some vulnerabilities are integration weaknesses, like allowing model outputs to trigger downstream actions without validation or allowing untrusted text to influence tool calls. Some vulnerabilities are operational weaknesses, like missing correlation identifiers and logs that make investigations slow or retention settings that erase evidence too quickly. Beginners should learn that classification is not just labeling. It is how you decide what kind of fix is needed and which team must own it. Clear classification also helps you avoid the mistake of blaming the model for a weakness that actually sits in the surrounding system. After classification comes prioritization, which is where likelihood and impact thinking becomes concrete. A vulnerability that is easy to exploit and could expose sensitive data to many users is typically higher priority than a subtle weakness with low impact. A vulnerability that enables unauthorized actions through integrations is often high priority, because it can cause real-world change quickly. A vulnerability that is rare but catastrophic may still be prioritized if the system is highly exposed or if the consequences involve regulated data or safety-critical outcomes. Beginners should resist the urge to prioritize based only on how scary a vulnerability sounds, because names like prompt injection can distract from whether your system actually has the exposure pathway that makes the weakness exploitable. A practical prioritization habit is to ask what is the easiest path to harm through this weakness, who could realistically take that path, and what would be the worst plausible outcome. You also consider how quickly the weakness could be exploited, because a weakness that is actively being probed deserves faster attention. Prioritization is the moment vulnerability management becomes strategic instead of reactive. Ownership is essential at this point because vulnerabilities do not get fixed by being known. They get fixed by being assigned. In AI systems, ownership can be complicated because the weakness might involve multiple teams, such as the application team that controls the interface, the data team that controls retrieval sources, and the security team that sets policy requirements. A good vulnerability management process assigns a single accountable owner for coordinating the fix, even if multiple groups contribute. The accountable owner ensures that remediation has a clear plan, that testing confirms the weakness, that changes are deployed safely, and that documentation is updated. Beginners sometimes assume security teams fix vulnerabilities, but in most organizations, security identifies, prioritizes, and guides, while engineering teams implement changes. That division of labor is not a weakness. It is how specialized teams work together. Vulnerability management fails most often when ownership is ambiguous and the issue becomes everyone's problem, which quickly becomes no one's problem. Clear ownership turns vulnerability management into predictable work rather than endless conversation. Remediation planning is the phase where you decide what kind of change will actually remove or reduce the weakness. The plan should consider whether you can eliminate the vulnerability entirely, reduce the impact if exploitation occurs, or improve detection so exploitation is caught quickly. For AI systems, remediation often involves tightening access boundaries, narrowing retrieval scope, reducing sensitive context injection, strengthening policy checks at input and output, and adding validation gates before actions are triggered. Remediation can also involve changing user experience to reduce misuse, such as requiring confirmation steps for high-risk actions or providing safer defaults that prevent sensitive data entry. A beginner should understand that remediation is not always a code change. It can be a configuration change, a permission change, a logging enhancement, or a process change like requiring review before enabling a new data source. The best remediation plans also consider operational fit, because a fix that creates extreme friction may be bypassed, recreating the vulnerability in a different form. Planning is where you choose a fix that is both effective and sustainable. A critical idea in AI remediation is to favor defense in depth, meaning you add layered protections so a single control failure does not recreate the vulnerability. If a vulnerability involves data leakage through retrieval, you might combine narrower retrieval scope with output filtering that detects sensitive data, plus monitoring that alerts on repeated probing. If a vulnerability involves prompt injection through untrusted documents, you might combine content handling rules that treat retrieved text as data with system-level constraints that prevent untrusted instructions from changing tool behavior. If a vulnerability involves integration abuse, you might combine least privilege permissions with validation checks on actions and a requirement for human confirmation for high-impact operations. Beginners should see that defense in depth is not about piling on controls randomly. It is about placing controls at different points in the pipeline, so the weakness is blocked in multiple ways. This matters because AI systems are complex, and complexity makes single-point failures more likely. Layering also helps during transitions because you can deploy one layer quickly as a temporary reduction in harm while building a more complete fix. The goal is to make the system robust, not perfect. Remediation also needs careful change discipline because fixes themselves can introduce new problems or can break important workflows. A fix that tightens retrieval can reduce data exposure, but might also reduce answer quality, which could drive users to unsafe workarounds. A fix that increases blocking might reduce policy violations, but might also block legitimate tasks, which can create pressure to disable safeguards. A fix that changes logging may improve evidence, but might also increase sensitive data storage if not controlled. Beginners should learn that remediation is not only technical correctness. It is socio-technical balance, where the fix must fit how people work so that safety is maintained in practice. This is why staging and gradual rollout can be useful, where you apply a fix to a limited scope, monitor for side effects, and then expand. It is also why remediation plans should include communication, so users understand what changed and why. When remediation is treated as a discipline change, the fix is more likely to stick and less likely to create new vulnerabilities through frustration. Verification is the step that transforms remediation from a hopeful change into a confirmed improvement. Verification means retesting the specific weakness, confirming that the exploit path no longer works, and confirming that related paths are not still open. In AI systems, verification often includes rerunning the abuse prompts or boundary tests that revealed the vulnerability, checking whether outputs still leak, and checking whether retrieval still overreaches. It also includes checking logs and monitoring signals to ensure evidence is still captured and that new alerts behave as intended. Beginners should understand that verification must be tied to the original description of the weakness, because otherwise teams can declare success while missing the actual failure mode. Verification should also consider regression, meaning you check that the fix did not break other safeguards or create new weak points. If the fix involved permissions, you verify that legitimate users still have necessary access while unauthorized paths are closed. Verification is where vulnerability management earns credibility because it shows that work produced measurable improvement. Documentation is an often underestimated part of vulnerability management, but it is essential for preventing repeat mistakes and for making decisions defensible. Good documentation records what the vulnerability was, what conditions caused it, how it was prioritized, what remediation was applied, and what verification confirmed success. For AI systems, documentation should also capture which assumptions were invalid, such as an assumption that a retrieval source contained only non-sensitive data or an assumption that a safety filter blocked a certain class of prompts reliably. Those assumption records matter because future teams may revisit the same area, and the documentation helps them avoid reopening the same weakness. Documentation also supports governance, because leaders want to see that risk is being reduced systematically and that residual risk is understood. Beginners should see documentation as a kind of institutional memory that keeps the system safer over time. Without it, vulnerability management becomes repetitive, where the same categories of issues are rediscovered and refixed because the lessons were not preserved. A strong vulnerability management approach also includes measurement, because you need to know whether the program is improving or just spinning. Measurements can include how quickly vulnerabilities are discovered, how quickly high-priority vulnerabilities are remediated, how often fixes hold over time, and how often the same vulnerability class reappears. In AI systems, it can also include how often policy bypass attempts are detected and blocked, how often sensitive data exposure indicators occur, and how quickly changes trigger reassessment. The purpose of measurement is not to punish teams. It is to reveal bottlenecks and to guide investment in better controls and better processes. If remediation is slow because ownership is unclear, you fix ownership. If remediation is slow because testing is not repeatable, you build a better test set. If vulnerabilities keep reappearing after model updates, you improve regression testing and change review. Beginners should understand that measurement turns vulnerability management from an anecdotal practice into a maturing system that learns and improves. It is also important to address the misconception that vulnerability management is only about external attackers, because many AI vulnerabilities are exposed through accidental misuse and internal change. A retrieval system that overexposes documents can be exploited by an attacker, but it can also leak data to normal users who simply ask the wrong question. A policy filter weakness might be exploited intentionally, but it can also be triggered accidentally by users who do not understand boundaries. An integration that acts on model output can be abused by attackers, but it can also create harmful outcomes through ordinary error if the model's output is trusted too much. Beginners should see that vulnerability management protects against both malicious and non-malicious harm. This is why discovery sources include user reports and monitoring anomalies, not just security tests. It is also why remediation includes training and safer workflows, not just code changes. When you expand your view beyond attacker stories, vulnerability management becomes more effective because it addresses the most common sources of real incidents. Finally, vulnerability management must be continuous because AI systems are living systems that change with usage and updates. A vulnerability that is closed today can reopen through a prompt template change, a model version update, a vendor feature shift, or an expansion of data sources. This is why the cycle from discovery to remediation is not a one-time project. It is an operational capability. Beginners should think of it as a loop that is always running quietly in the background, catching weaknesses early, guiding improvements, and verifying that safety boundaries hold as the system evolves. Continuous vulnerability management also supports safe innovation because it reduces fear. Teams can move faster when they know weaknesses will be discovered and addressed systematically. It also supports trust because leaders and users can see that the organization does not pretend it is perfect, but it takes responsibility for reducing risk over time. When vulnerability management is continuous, security becomes less reactive and more stable, which is exactly what modern AI systems require. As we close, building AI vulnerability management from discovery to remediation means creating a reliable cycle that turns weaknesses into verified improvements, instead of letting weaknesses accumulate until they become incidents. Discovery is continuous and grounded in real system behavior. Validation makes issues precise and reproducible enough to fix. Classification and prioritization keep effort focused on realistic harm, and ownership ensures work actually moves. Remediation plans must fit the model, data, and use case, often using defense in depth to close pathways at multiple points in the pipeline. Verification proves the weakness is truly reduced, documentation preserves lessons and assumptions, and measurement keeps the program improving rather than spinning. When you treat vulnerability management as an operational capability, AI security becomes more predictable and resilient, because the system can evolve while controls and confidence evolve with it. That is the practical promise of Task 7, not perfect safety, but disciplined improvement that keeps trust intact as the technology and the organization keep moving.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.